Hello, good afternoon, everyone. So today we're gonna continue talking about unsupervised learning, where we left off last time. We wrapped up a discussion about k-means clustering. And one of the, I guess, downsides, or somewhat of a downside of the k-means clustering, I think, which was somewhat highlighted at the end of last class, is that you have to pre-specify the number of clusters for the algorithm to work. And there's some subjectivity in actually deciding how many clusters there are. So there's this alternative method known as hierarchical clustering. Okay, this is way too thick. This is also known as either bottom up or agglomerative clustering. So this alternative method does not require pre-selecting K. And this results in a tree-based representation known as a dendrogram. Okay, so I will draw an example tree, and then we can go through some of the nomenclature related to the tree. So let's draw something like this, and then maybe something like this. Okay, and generally, so the farther up the tree branch, the farther up the tree branch's fuse, the more different the leaf observations are. Okay, and so your individual points are here, and so these are what we refer to as the leaves. And I can cluster the leaves on my tree based off of cutting the branches at specific points. So the thing about the hierarchical clustering is that it still requires you to make a decision about how many clusters that you want, but it preserves all the information about grouping of all the clusters. So if I were to make a cut right here, this would give me 2 clusters. If I were to make a cut right here, this would give me 3 clusters. And if you were to cut over here, this would give you 4 clusters, and so on and so forth. And I can always make, well, actually, hang on. These should need to extend all the way down. And I can always, I should always be able to make anywhere between 1 to n number of clusters where n is equal to the leaves on the tree. Okay, all information about the clustering and the design of the dendrogram is based off of vertical information. And so no conclusions can be made on distance horizontally. And therefore, I don't know anything about whether or not C or D is closer to B, because that's all based off of horizontal distance in the same branch. Okay. So the algorithm to design the tree is actually fairly straightforward. So each observation is its own cluster. So let's say we have n total. Then the two most similar are fused. So you have n minus 1 clusters. Repeat until a single cluster is left. Okay, and so what does that mean, the two most similar? So there are a couple ways we can do this. So similarity on basis of Euclidean distance. And so this works for individual points. Okay, so if I were to do a graph, and remember, again, just to reiterate, this is all unsupervised learning, so we have no response variables. We're just looking at how different variables relate to sort of one another. So if I have a point here, and a point here, and say a point here, and here, well, I can figure out the pairwise distances here. For this guy, it would be here. For this guy, it would be here. And for the last guy, it would be like this. And I can pretty easily identify the fact that these points are the most similar. So if this was A, B, C, D, well then A, B, C, D in the tree, I'm going to connect these guys first. Okay. And that's the similarity on the basis of Euclidean distance. But now we've got something a little bit more different going on, because I can, let me erase all of these points. Oops. So if you group these together, okay, I still have some information about C and D distance, but then where are these going? So the other metric for similarity is based on linkage to the branch. And so this is, there are 3 ways to do this. So 1, complete. This is the largest dissimilarity. Okay, so what that means is, let's take an example of, let's look at, oop, did not mean to do that. Let's look at C. I've got this and I've got this. Let's say that this length, let's say the Euclidean distance is 5 and this is 6. And therefore, the 6 is a larger distance, so it is less similar, and therefore I will choose 6 as the sort of next sort of set of distances that I'm going to compare. You could do a single, what's known as a single linkage, and this is the smallest dissimilarity. And so in that case, well, so this would be like in green. Okay, if we do in red, it would take the smallest one. And then let's say in blue, the last one would be the average linkage, which is the average dissimilarity. Okay, and so the blue would be 5.5 distance. Okay. And so what ends up happening is you will likely have something that ends up looking like this.
I have a quick question about the average.
Yes.
If you're comparing to 3 points, is it averaging the distance to all 3, or just the difference between the smallest and the largest?
Averaging all 3. Yeah, it takes the average Euclidean distance to all of the leaves in the branch. And what you'll tend to find is that average and complete linkages tend to have more balanced clusters. And we're going to see an example of that and how that sort of balancing works out. All right, any questions about this? Okay. So I guess I'm only bringing this up because I've recently been sort of employing these kind of algorithms to sort of really large scale data sets. And one thing to note is that the number of combinations of like distances that you're looking for can explode pretty quickly. And so at really large scales, the k-means clustering is actually a really efficient way of doing it. And the hierarchical clustering tends to be a fairly intensive computation procedure. So sometimes it can take a little bit longer to run. And the other thing is that you need to, generally the way this works is it takes in a similarity or dissimilarity matrix that has pre-calculated all of the pairwise distances between all of the points. And that matrix, once you're dealing with really large data sets, can be really memory intensive. So that's one possible kind of shortcoming to keep in mind. We were struggling to do this problem where we were doing pairwise distances of something like 5,000 zones in California, which ends up being like 25 million pairwise distances, and that is really difficult to kind of hold in memory as a 2D matrix. Okay, so let's take a look at a smaller example than that. So let's jump on over to R. And we're gonna go ahead and just use the same example from last class, which was looking at the auto data set.
I think your screen is frozen.
Oh, of course it is. 1 second. Stop sharing. And let's try that one more time. And of course, it's going to take like 10 minutes for it to load. But I'm just going to continue writing in some of the code from last time, which you guys should actually be able to just copy and paste. As it loads. The most exciting point of the lecture right here. And actually what I'm typing right now is, again, just kind of loading in the data from last time. And one of the things that I am actually including is the scaled. If you look at the last lecture's code, there's this auto scaled thing, which is normalizing the values of the variables that that I'm trying to cluster on. And so if you remember, it's going to be miles per gallon and horsepower, and miles per gallon is on the order of like, 10 to 50, whereas horsepower is on the order of several hundred. And because the clustering, again, is based off of Euclidean distances, in the cases where you care about the relative distances between each of your variables, then you're going to want to normalize them against each other or scale them so that all of that will be sort of equally weighted across variables. Again, this is context dependent because there are situations in which you may not want to do this normalization. So think carefully about how you want to be doing your clustering in that case. So here we will be doing this normalization. And
could you maybe copy and paste your code into the?
yeah, that's a good idea. So this is what I have so far. I'll just. Yeah, and everyone should be able to recognize this set of code from last time. I guess that's going to be one way to do this. If this never loads, I'll just copy and paste it, and then you guys can run it on your end. So the next step is to actually just run the function. I know that you guys still can't see, so I will copy and paste that code in just a moment so that you can see. Okay, so the algorithm is built into this function called hclust. Oh, here we go. So what I just copy and pasted were these 3 lines of code. So dist is actually, let's go ahead and just take a look at what this does. So if I run this, okay, this is what we're going to try and cluster. And let's see here. Auto.scaled. So here's the scaled or essentially the normalized version of my 2 variables, so that the distances will all be relatively the same across these two variables. And then what I'm actually passing into hclust is not that. I'm actually passing a distance matrix, which you generate with this function called dist. And we can see what this looks like. Maybe. Actually, I'm actually gonna see if I can save this explicitly. And then we'll just replace that just so it's extra clear. Okay, so 392, there are 392 data points within auto. If I look at the distance matrix, this is going to give me the pairwise distances between every set of points. It's not actually going to let me look at this, huh? Okay, so 392 squared, 153, 664. So if I have a distance x1 to x2, that tells me the distances between both, so I no longer need x2 to x1. And so what you can see here is that this matrix is just, the distance matrix is the full matrix of pairwise comparisons minus all the ones along the diagonal, which are like x1 to x1, x2 to x3, so those distances are all just 0, minus the mirror distance, so that you don't need, so if you already have x1 to x2, I don't need x2 to x1 because the distance is the same. So the size of that is going to be around 76,000, which is what we see here. So hopefully everyone can kind of like visualize what the distance matrix is telling you. And then we've got, so we're passing the distance matrix to this h-clus function, and then we specify a linkage method, complete, average, and single. Again, right, this is just looking at the group of leaves in the branch and taking, if it's complete, it's going to be the largest dissimilarity. If it's average, it's going to be the average of all the leaves in the branch. And then if it's single, it's going to be the smallest dissimilarity. Okay, so I'm going to run this. And let's take a look at the trees themselves. Okay, so I'm gonna actually plot all of them at the same time so we can see how different the trees look. This is important to understand how the choice of linkage affects the clustering. Let me see if I can. Do this. Actually, give it one more moment to clear and then rerun. But even here, hopefully you guys can see. Well, all right, we'll let it rerun. There. So this tree has, you know, about 300 to 400 points in it. So you can already see how kind of crazy it can get when you have, you know, this many points, because the tree breaks down to the individual leaves, and you can imagine you know, once you're getting to the thousands, it becomes pretty kind of infeasible to look at them like this. But anyways, I think that for what I was mentioning in the notes is that the complete and the average tend to have the most balanced clusters. And so as I take some slices, you know, if I were to go across here or across here or across here, when I mean a balanced cluster, it just means that the number of leaves, branches and leaves within a specific cut is going to be, you're going to have like a similar number within each of those cuts or each of those clusters. Whereas with a single linkage, you can see that like here, for example, if I do this cut right here, the one on the right contains like 90% of the points, and the one on the left contains just a small handful. Like I can actually see it from here. It's like 1, 2, 3, 4. Like there's going to be like four branches that contain, you know, a really small sort of number of the final number of points. Okay. So let me clear this away. And let's actually go ahead and look at the assignments. So there is, I'm going to go back into the original data set, kind of like what we did with the k-means clustering, and I'm going to create a new column called hc.clusters. So HC for hierarchical clustering, and it's going to be .2 to indicate I'm going to pick the one with 2 clusters. And the way that you do this is with a function called cut tree. So all you need to do, so what we're going to do is we're actually just going to, actually I'm going to do it like this, complete. So I'm going to pass the information about the model in HC complete into cut tree, and I'm going to specify I want 2 clusters. So it's going to cut the branches at the right point so that you have 2 clusters, and then it will assign the points. And so that will look something like this. And I will just go ahead and plot it. And this will look like this. And so these are the 2 clusters. Let's see what that looks like for the single linkage. I'll just copy and paste this and change this to single. Oh, I need to run this first, and then so that part still looks kind of similar, but if I were to, let's say, let's go up to 20. Let's take a look at what these look like. Don't know if I've ever done 20 colors before, but let's see what happens. Okay, so this is with the complete clustering linkage for the hierarchical clustering, and you can see how it's breaking down these points. And let's see if the single one looks any different. Okay, in this case, well, I don't have them side by side, so harder to tell. But typically, you're going to start to see like larger and larger groupings of points with the single. I would say most commonly when I've seen applications of hierarchical clustering, most people will do either complete or average linkages due to the fact that it's that you have more balanced clusters. But I don't do a huge amount of work in this area, so you know, I can't say that single linkages are necessarily like a bad thing. Okay. Why don't we stop here for our break for 5 minutes? And yeah, I will be here to take any questions in the meantime.
Professor?
Yes.
I have a question about this graph. Like in this case, how would you interpret this graph in terms of these like variables? Like let's say I employed this technique for a project or something.
Yeah. So I think the most important thing to have in your mind about this is that we are doing unsupervised learning, which means I basically want to figure out what groups of points kind of quote unquote belong together. This particular example is maybe a little bit arbitrary because we're just looking at like MPG and horsepower. And the kind of meaning behind that might be a little bit less less straightforward. But if I could, I can maybe give you an example of the project that I was working on that deployed this. Okay, so we'll get into a little bit of a sort of aside, but I can give you kind of the context behind you know, what types of problems might you want to use like a clustering algorithm like this. Okay. So the project that I'm working on is trying to figure out how to deploy fueling stations. This is actually specifically for hydrogen. So let's say you have a whole bunch of, regions. And then let's say we have some kind of process that calculates routes to go from, you know, point A to point B, and that you actually have many routes. You you know, because you have routes going to different locations. Kind of like something like this, okay? And I want to pass information about how vehicles are using these routes to make trips. So let's say that you actually have vehicles going on each of these red lines. And then I could pass into some big model all this information about, okay, this is route A, B, C, D, E, F, and so on. So the reason why you need to pass all of this route information is because it needs to know, oh, there are some number of trucks going on route B, some number of trucks going on route C, some number of routes going on route D, and they all go through certain regions. And I'm going to place a station in a place where like you have most of the routes intersecting. The problem is that maybe you have on the order of let's say like 10 to the 6 routes. And so the model that we're passing this to is this optimization, and it's like it becomes way too complicated. But one of the things that you'll notice is that routes B, C, and D, they all overlap with one another a lot. And in fact, B and C overlap with one another even more, right? Or it should be drawn up to here. So there's this question of, okay, can I kind of like combine routes together in a certain way so that it looks like I'm only passing some number, a smaller number of routes, and can I reduce this down to 10 to the 5th, 10 to the 4th, 10 to the 3rd, which would really help it. And what we ended up doing is, okay, I can look at the number of overlaps, and that's essentially like a similarity matrix, right? Because if I count the number of overlaps, I can then pairwise for every route say route A and route B overlap by 1, route A and route C overlap by 5. And so you can treat that as a distance matrix and then cluster routes based off of how often they overlap. And then you essentially create this giant tree, and we're then able to cut it at a specific point so that I have like a much smaller subset of like routes to work with. And then you could just add up all the demands for the intersected routes. So, okay, that's kind of like a long-winded example, but the whole idea is if there are contexts of problems where you need to do some kind of grouping, then clustering provides like a quantitatively backed approach to essentially putting objects together. So I think that this particular example is like a nice, hopefully clear application of it, you know, as opposed to the kind of application that we see that I gave in the class example, which is more kind of an arbitrary way of kind of executing the clustering on kind of an arbitrary data set. Does that maybe help a little bit? Or are you still kind of confused on? how you should be using this. Sorry, what was that?
It does. Thank you.
Yeah, okay. Okay, good. Yeah, it's I think like jumping to unsupervised learning in general is definitely kind of a leap from what we've been doing before, because it's all the types of problem where you do like clustering are generally going to be a little bit different than what you're trying to do with regression problems. Not always, but generally, I think that they're fairly different. So. Alrighty. Yeah, I think that those tools are kind of handy to keep in your toolbox anytime you run into problems of this sort, because yeah, they're really handy in being able to do this kind of grouping. Okay, we're doing kind of a whirlwind tour here. That was actually all supposed to be part of the whole last lecture, but you know, hierarchical clustering does take a little bit longer to go through, I guess. But we're actually going to jump back into the world of supervised learning. But as I was mentioning before, we're going to start delving a little bit into more classical machine learning methods in approaching some of the types of problems and strategies that we've been going over in class. And so today, what we're going to be talking about is thinking about supervised learning, specifically for classification. And so this was all of that stuff that we did with logistic models, with LDA, and then starting to touch into some of the sort of non-parametric approaches with the KNN. And so today we're going to be talking about something called support vector machines. And we're going to kind of build up to that in, I think, a nice sort of qualitative step-by-step procedure where we're looking at essentially how to do sort of a classification by creating these sort of separators or boundaries about points that will let us that really will just focus on prediction much in the similar way that KNN does. And so the inference part of this actually is kind of possible, but realistically, you would never try and do inference from the sort of techniques that we're going to be talking about today. So the first thing that we're going to introduce is a hyperplane. This is a flat affine subspace, subspace of dimension p minus 1 in p dimensional space. Okay. Don't worry too much about the formal definition. Let's draw some points. This is a hyperplane. It's just, it'll extend out into sort of multiple dimensions. Here, it's an example in 2 dimensions. We have x1 and x2. So in 2 dimensions, we can define this hyperplane like so. So this is in 2 dimensions. Generically, in p dimensions, it will look something like beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 beta p xp. I should maybe even use a different variable than beta, because this is describing a line, right? And you may kind of think about this in the context of the regression, but it's not like that, right? Because we're not really fitting this line to the points. So the betas are not calibrated to this whole least squared errors type thing. Okay. So let's talk about the maximal margin classifier. So this is an optimally separating hyperplane. So separating hyperplane that is farthest from training observations. And actually, let me give a little bit of context. Oh, not here. Let me go back to this one. The reason why we make this hyperplane is that it allows us to do predictive classification. Because if I train this hyperplane on these points, I can then say something like everything on this side is going to be blue, and then everything on this side is going to be red. So that's essentially what we're trying to do here. However, you'll note that in that particular example, well, okay, let me just draw a slightly different one. Let's say we have points like this and some points like this. So I've actually got a problem here in that I can draw a hyperplane like that to separate my points. But I could also draw a hyperplane like that, or a hyperplane like that. And in fact, I could actually draw an infinite number of hyperplanes that could clearly distinguish the boundaries between all of these points. So that doesn't help us to really figure out where to draw this line or hyperplane. So there are an infinite number of separating hyperplanes. And so the way we deal with this issue is I can figure out how to draw a line that will maximize the distance between all of the points. And this line is known as a support vector. The math behind it is not so complicated, and I will write it down for your reference here. Beta P, comma M. So you're maximizing this quantity M with constraints such that, so the sum of my beta squared is equal to 1, and yi times beta 0 plus beta 1 xi1 plus beta 2 xi2 . So it's just an optimization with these set of constraints. And this will then allow you to select a single hyperplane known as the support vector that will maximize the distance of each of your points to that hyperplane. And that allows us to solve this particular issue of an infinite number of hyperplanes to draw. And maybe you guys are already kind of thinking of this, but you've still got some substantial issues in the sort of in the use of a maximal margin classifier. And so let's talk about some of these. The most obvious one is non-separable cases. And so this is the most common. Okay, this is what we had before. And you draw a hyperplane to separate these. I put one more point in here and bleh, it no longer works. Right? There is no hyperplane that I could draw through the points that would clearly separate the red points from the blue points. The other issue is a little bit more nuanced, but also an important one. Sensitivity to individual observations. Okay, I need to draw this one a little bit more carefully here. So let's see. replicate that over here. So in this case, in the left, I might have something that looks like this. And you have your distances like so. If I introduce a single point, it may cause my line to decrease quite a bit. Yeah, so I think looks something like this. And in this case, what you can see is that the boundary is really significantly affected by the introduction of individual observations. And that can be a sort of powerful downside to the maximal margin classifier because its sensitivity to individual points can really make a large difference in your like predictive power. Okay, and so when we go from the hyperplane to the maximal margin classifier, that's our kind of first step to deal with some of these fundamental issues about an infinite number of hyperplanes. The next step is to go to what is known as a support vector classifier. And much in the same way that we kind of evolved from a simple hyperplane to the maximal margin classifier, here what we're doing is we're going to add general robustness to individual observations. And we're also going to do better classification of most training observations. And the way that we do this is same optimization as the maximal margin classifier, but with one additional constraint. Or actually, it's not one, but with additional constraints. We're going to have a new term, epsilon I greater than or equal to 0. And then a constraint I equals 1 for each of my epsilons less than or equal to C. So this is a tuning parameter. And when I say tuning parameter, you guys should get some warning bells in your head about, oh, how did I choose the tuning parameter? And likely it's going to be through some form of cross-validation. And so we're going to modify one of the constraints this one. And we were saying before that it's greater than or equal to m, but this time we're doing greater than or equal to m times 1 minus epsilon I. And so this epsilon is known as a slack variable. And so let me describe what these are doing. So your epsilon I tells you how many points can violate the margin. And C will tell you the bounds for number of epsilons. Oops, sorry. At C equals 0, it is the same as your maximum margin classifier. Okay, and so what the support vector classifier will then allow you to do is, if I were to go back on over here, you could, in theory, draw a hyperplane now here where you would violate this, you would violate the separator because you are given this slack variable as a sort of budget for sort of breaking that. And so that would then allow us to draw hyperplanes in the cases where you don't have separable cases. But importantly, it also reduces the sensitivity of your hyperplane position to individual observations, because it basically allows you to violate that maximal distance in the optimization. Okay. Any questions about this so far?
I didn't quite get what you mean by bounds for numbers of epsilon i's.
Oh, yes. Okay. So let's go back here. What this is doing is it's acting as a budget for violations. So our epsilon I is a measurement of how many points violate the separator. So let me go back to this. So in this particular, when I say this, so I'm going to talk about this graph here. In this particular case, our epsilon I is equal to 1 because you have 1 point that is on the wrong side of the separator. And then if I were to do something like that, then that would be epsilon I is equal to 3. Okay, and so the C is going to tell you how many violations you're allowed to have. Okay, and so if, for example, if I were to adjust it so that C equals 3, here, let me draw it with this. Oops. Let me fix that really quick. Okay, so let's say C equals 3. Well, then I will choose something like this, and I will have my 3 violations and then minimize the distances for the rest of the points. If I did C equals 2, well, then I'm no longer allowed to do that. My line will now look like that. And I will have 2 violations instead of 3 violations.
That makes sense. Thank you. So it acts as an upper bound, right? Because we said that sum of epsilon I is less than or equal to C. So it doesn't have to be 3, but it can be at most 3.
Yep, exactly. Okay. So downsides, it must be linear. Let us consider now a different set of points. You could even have like a super obvious set of boundaries. And like ideally, I would draw something like that. But unfortunately, I end up having to do something like that. Or like that, depending on whichever one kind of, well, I guess it'll be like this one because that's the one that minimizes the, or sort of maximizes the distances. So unfortunately, with the SVC, it must be linear. So the next step of improvement is to do support vector machines. So this is kind of our final step. So we could allow for polynomial expansion or interactions of x's. So this would be something like y equals beta 0 plus beta 1 x1 plus beta 2 x1 squared plus beta 3 x1 cubed, right, and so on. And then you'd have it for x2 as well, x2 squared, and so on. Or you could do something like beta 0, beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x1 x2 plus beta 5 x1 x3 and so on. Okay. So unfortunately, even with a very small number of variables, this rapidly becomes infeasible. In a similar, we've had this discussion before of kind of the, the size of this will grow to the end. So adding polynomials and adding interactions lets your lines start to get more and more flexible, but the complexity ends up being really, really too a little too crazy. So instead, you can modify and generalize the computation of the SVC. So SVC uses a linear kernel. SVMs can employ more complex kernels. So this can be polynomial or radial are two examples. And when you do polynomial, they don't go into very high orders, which is why you're able to keep some feasibility here. So I'm not actually going to get into the sort of math behind this, but all you have to realize is that the kernel's calculations for the computation of the support vector classifier are essentially generalized that allow you to turn your hyperplane from a linear form into kind of like really flexible shapes. And so we're going to look at an example of this now, unless anyone has any questions. So we'll jump back on over to R. And I'm going to load one more library. We're going to actually look at an example from this data camp here. So let's take a look at the SVC first. So folks can actually follow along with even though we're doing some random draws here, it's going to be set to a seed, which allows you to pick a specific set of draws. And let's just look at this plot to see what's going on. Okay, so we've got this set of points over here. I'm just going to make this into a data table. And my Y's are just a separated factor indicating essentially red or blue, so that you're grouping your points in a certain way. So this is exactly what we're kind of talking about when we're referring to like the traditional classification, right? When you have discrete variables, we're just representing those discrete levels as colors, as red or blue. This could be like flipping a coin, heads or tails, for example. So we're going to create a support vector machine generalized as so y getting regressed on x. I'm putting the dot here to make it grab everything, but it's just x. Grabbing the data from this data table. So far, kind of similar to most of the models that we've done before. And I'm going to add in a kernel, like I was saying, linear. I can put in the cost, which is my C variable. That's the slack. So it's going to allow it to get up to a total of 10 violations if it wants. So I'll run this. Oop. And let's do a summary SF SVM fit.linear. Oop, SVM. I'll do it like this. Okay. So it tells you number of support vectors, 6. That's the number of points holding up the line. And then there are 2 classes. So let's take a look at a plot of that. Great. So we can see here, this is my hyperplane. It's just a straight line. I guess there's some kind of rounding thing going on here in this plot. Oop, I see a question. Which library is SVM in? It should be, I think it's in the E1071, but let me double check. Yeah, so this package here, E1071, that's not a default package, so you'll have to install it like so. And I can see my 6 support vectors. That's going to be 1, 2, 3, 4, 5, 6. And then it's got my separated into your 2 classes. And so once you've drawn this line, I can then in the future kind of make predictions about how to classify points that lie on sort of either side of the boundary. So importantly, so this is going to get the sort of one parameter that really affects the location of the line is my slack parameter, the C. And so when you calibrate this, you can mess with that. And then you could actually give preference to errors for type 1 and type 2 errors, kind of like what we were talking about before. Anytime you're doing classification and you're doing calibration according to mean squared error in the classification side of things, you care about how often you're getting a particular guess right and a particular type of guess right. And so you could be really conservative, like if you wanted to get circles. So if you wanted to reduce the errors for the circles, you could do it you could draw your line in a certain way, or if you wanted to reduce the errors for the X's, you could draw it in a different way, versus if you want to just get the total number of errors. Okay. So now let's look at a support vector machine using a radial kernel example. So I did put this in Canvas already. There's a file called ESL mixture. So we can look at what's in here. You've got some set of X and Y points. And let's see. Let's see what that looks like. So I'm actually going to remove our original X and Y and then attach these so that each of these will be their own sort of object. And I'm just going to overwrite, remove the ones that exist already. We're going to create our data table again. And actually, let's plot this first so we can see what this looks like. It's just so that I can get this unique set of points here. Okay, so we're now looking at a plot with a fairly more complex set of points with obviously is going to be a sort of a lot higher a lot higher number of violations. I should also mention that the C in the equations, as I was saying before, which is the tuning parameter that allows you to have some slack in the system for number of errors, that is related to the cost that you specify in the SVM function, but it's not, it is not the sort of only, it is not necessarily the direct number. And the reason why they do that is it is to do it as across a scale is because you may have like a really large number of points and you don't know how many you want to be getting violated. So it makes more sense to scale it from sort of an arbitrary scale as opposed to specifying the exact number of points that you want to be allowed to violate. Okay, so we're going to fit this new one. We're just going to use a radial kernel this time, and I'm going to put a cost of 5. Let's look at the summary. And let's go ahead and plot it. Okay, so there's 103 support vectors. Okay, there's just a lot more points in this case. 2 classes, and let's have a look at this. Okay, and what you can see is that by having a radial kernel, which essentially allows for you to do single level interaction between your variables, I am able to create a hyperplane, that a nonlinear hyperplane that can sort of wrap around these points in this manner. And so we can see here how the classification then allows you to do predictions for your X's or your circles based off of the separation of the hyperplane in this 2D space. This, if we kind of go back to the logistic and LDA examples, you remember that we are creating these sort of linear boundaries, and that is a function essentially of the functional form of both of those models. And then when we do a sort of non-parametric approach with the k nearest neighbors, you were able to now get much more much more sort of nonlinear boundaries. And that's kind of the case here. I would call this more of a semi-parametric case because you still have your x's being defined within parameters that are created by the kernels, in this case, the radial kernel, that help you define this plane. But you can see that in this case, it's definitely not like a straight line of any sort. It allows you a lot of flexibility in selecting how that line can be drawn. And again, depending on how you decide to classify your or how much weight you put into certain types of errors, that line itself could be drawn pretty differently. Yeah, so if you want like, if like x's are your positives and circles are your negatives, you might prefer to have a high, you might have a much higher preference for having low positive error or false positive errors versus low false negative errors, right? We've discussed about why you might do that, which would cause it to favor doing error exceptions for circles versus x's. Okay. So that is our application within R of doing support vector classifiers and support vector machines. Any questions about the lecture material?
I have a pretty basic question. So parametric techniques, from what I understand, are when you kind of assume the underlying population is normally distributed, right?
No, that is a type of parameterization, but generally speaking, models with parameters are just like anytime you have like these like betas associated with your x's, your variables. Okay, that's like a really big generalization, but you're assuming some kind of functional form, right? Whether it's like a line or some kind of curve, as opposed to our really sort of non-parametric approaches, such as your KNN, or even the kernel method. Those are both good examples of non-parametric equations where you don't have parameters specifically associated with your x, with each of your variables.
Thank you.
Yep.
I have a question about, so we set the cost equal to 5.
Yep.
And maybe I'm a little bit confused, but I thought that the cost was equal to C, which is the cap that we put on the number of points that can be.
Yeah, that's what I was saying. Yeah, that's what I was trying to mention earlier, is that the cost is related to C, but it's not directly equal to C.
Okay, I think I didn't exactly understand that part. If you could repeat it.
Yeah. So the cost is essentially, you can think of it as like a scaled version of C, so that it can be generalized to many problems, and you don't have to say exactly how many violations that you want. So in general, I believe the higher the cost, yeah, I think it corresponds to having a larger slack. Yeah, I should double check that, but it generally what should be happening is that at higher cost, it's equivalent to allowing to have a larger number of violations, but not like exactly the quantity.
Okay, so I was looking at the help page for the SVM function, and it was saying that the cost is the C constant of the regularization term in the Lagrange formulation. Is that just something that?
Yeah, that's right. Hang on. So that is the C that we're talking about, but it shouldn't be exactly the same. I mean, it obviously isn't in this case, right? Because we have way more than 5 violations. Let me see if they have the equation. No.
That's okay. My primary question was just kind of seeing, because obviously I saw more than 5 points that didn't fit exactly, so I was curious about that relationship, but I do think it's helpful that.
Yeah, let me check this and get back to everybody, because what I have in my head about this is that the cost is essentially a scaled version of the C, but the help package is saying that it's equal to C, which doesn't make sense because obviously there's more than 5 here. So yeah, let me check that and then get back to everybody.
Okay, so I kind of a follow-up question. If say that cost was equal to C and we had set it to 5, but it had to misclassify or incorrectly classify more than 5, would it still just fit it even though we told it only 5?
So there are 2 ways that it can deal with it. One, it could just say it's infeasible, but most algorithms now have some kind of like penalty constraint that will get like essentially larger and larger for more number of violations. And so it can actually still go above. And it's treated, it essentially, in the optimization, it treats it with a slack variable that lets it go up, and then it introduces a larger penalty function into your objective function. So let me, yeah. So the one that I kind of introduced in the notes, those equations are specifically this this hard constraint because the epsilon is directly tied to your tuning parameter. But it may be the case that in this particular formulation, that instead of having it as a hard constraint against your slack variable, that it is a penalty constraint that just goes into the objective function. So again, I will double check that and we'll clear this up next time.
Okay, sounds good. Thank you.
I have a general question, like how do we decide to scale the data or not?
What do you mean?
For the last case, you did the scaling in the SVM, right? And then for this one, you didn't. I just wonder, like, how do we decide about that?
No, okay, I think.
Oh, no, you didn't.
I think in both cases they're not scaled because you're choosing. I'm pretty sure. I haven't checked this myself, but the scaling generally is similar to actually what we were talking about before, when you have variables that are really different in magnitude. Like if we're doing like the MPG horsepower type of thing, the whole issue is that the support vector is based off of distance. And so if you don't do scaling, it may, in some contexts, much more favor one particular variable and not care about your other one as much. And so that's, in this case, I don't need to scale because they're the same. Yep, yeah, that's exactly what it's doing. Yeah.
Okay, so both the support vector and the MMC, like all these methods actually depend on the distance a lot. So usually we need that it is of the same scale.
Yeah, usually you would want to scale them. Again, depends on the context of your problem. It is possible that you would choose not to, but usually you do.
Okay, thanks.
Mm-hmm. Okay, so that is all I have for today. So let's end a little bit early. And we will stop here.